All right. Nice ceiling, Stasia. Hello, Brandon. Eric, Luca.
Hi, Mr. Fowl.
How we doing, Mr. Lee?
Good.
Excellent.
Me? Or is this...
No, you're just Eric Lee. It does not have your picture. I don't have Madison, Luca, or Eric. And Natalie and Anastasia are just showing me their ceilings.
Hi.
There's Natalie.
Oh, wait, I don't think I enabled it.
Okay, now I hear.
There's Anastasia. There's Brandon.
Hi.
Madison. Emma.
Hi.
Oh, you just woke up. I'm so glad I joined you in the morning. Oh, great. Excellent. I love that you have a globe in your room, Madison. I love it.
Andrew.
All right, so I'll wait like another minute or two, see who else is joining here, and then we'll start.
What are we doing today?
We are gonna do, we'll go over the notes on half-lives and how you figure out elementary steps and intermediates, and then we'll stop. So I don't know, 20 minutes, half hour at the most.
Oh. I thought I just heard we're going to learn about headlights and we're going to learn elementary stuff.
No, it is elementary stuff though. You'll be good. We'll be good. And I'm trying to figure out more. Oh, I think I'm yelling. I'm sorry. I'm trying to figure out more about the test, the AP test.
Oh yeah, because they like changed everything.
Right. Somewhere I heard, and I gotta like figure it out. It might only be FRQ.
I wouldn't be mad at that.
Because I think if they're making you, from what I heard, they're not letting you guys take it in person, potentially. So if you're taking it at home, they can't not make you use a calculator. So then multiple choice questions don't work. I'm not sure. Braden, I'm so glad you're at school still. How did you get inside?
I snuck in through your upstairs window.
Man.
Guys, we should sing happy birthday to Jose.
Oh yeah.
If he joins, we gotta tell him to join.
Yeah.
I also enjoy, Braden, that you're sitting the wrong way on the chairs like a cool guidance counselor.
Yeah, I couldn't find a another picture.
It worked. You could just be talking over James Harrison. That would also work. And Eric's in a comfortable bathrobe. All right. Let's start. So let me know if you guys see. You see zero rate law?
Yeah.
All right. So if you're muted, you can unmute yourself if you have any questions. Don't hesitate just to ask and like shout it out because I can't see everybody all at the same time or anything like that. All right. So we don't really need to write, you know, if we look at this, we can kind of figure out that the rate law is zero because A, it tells you that it's zero at the top. But the other way to know that it's zero is no matter what happens to the concentration of ozone, what does the rate do? You can say it out
It
loud.
stays the same.
Yeah, it stays the same. So if you think about it, if you were to solve for the rate law, that would mean the exponent would be zero. So hence it's a zero rate law. The only thing you need to know about zero rate laws, you don't need to write down either one of these equations. The only thing you need to know about zero order rate laws is that their half-lives get shorter as the concentration decreases.
Wait, Mr. Fowl, are these notes on Google Classroom?
Yes.
Okay.
Yes. Sorry, I forgot to tell you that. Yes. Give me 1 sec, Mike. Give me 1 sec, guys. Sorry, guys. Okay, so again, for zero order, the big thing to remember is that, all right, half-life doesn't, the half-life for how long it takes for half of something to go away. For zero order reactions, every consecutive half-life is shorter than the one before. That's all you need to know about zero order reactions. So if you started with like 1 mole of something and it took 10 seconds for half of it to go away, the next half-life it only take 5 seconds, and then the following half-life it only take 2.5 seconds. So every half-life is half the time. Zero order really doesn't show up. They don't give you either equation on the test, but you might see a graph for it. I doubt it, especially in this year's test. Okay. First order. Both of these equations are given to you on the equation sheet. They will test you on first order reactions. This is the big one. This is the one you definitely need to understand. So if we look at the, I don't know how to draw a straight line, whether it's with a real marker or a mouse marker. Oh my God, I'm done. I'm not trying again. All right, with this guy, the integrated guy, if you take the natural log of A, that would be the post half-life concentration, and you graph it versus the natural log of the initial concentration, A naught, you will get a straight line. So if you ever see one of the axes as the natural log of A versus the natural log of A naught, and it gives you a straight line, that is a first order reaction. So again, if your X and Y axes are natural log of A and natural log A naught, and the slope is straight, it is first order. Okay. As far as half-life is concerned, the half-life for a first order reaction does not depend on the concentration. Therefore, the half-life is always the same. Do you guys remember doing the radioactive decay last year when you guys did like the licorice half-life lab?
Yeah.
Yeah.
That's first order. All nuclear decay reactions are first order. All right, so let's try this out. So a first order reaction is 35% complete at the end of 55 minutes. What is the value of K and their half-life? So we'll start by using, right, the integrated equation. All right, and I'm gonna go to a clean slide and try to write as best I can. So please bear with me. All right, draw. All right, so we would do, all right, oh my God, natural log of, so we can make A naught any number we want to, and the easiest number would be to make the starting value what?
One.
1. But A is what's going to happen after the reaction is over. So how much of the reaction preceded? It tells us on the slide.
65%.
Does it say 65% was already done, or that's what's left over?
Well, it said 35% was left over.
Okay, so 35% is left over. So we would have, right, so our new amount would be 0.65, correct? Equals, all right, negative K. Time can be any unit it wants. We'll just have to keep that in mind when we label our units for K. So we can keep K as T as 55. Yeah. Plus the ln, and then the initial amount was 1, so the ln of 1. All right, so let's solve for K. I got 0.007 heat. And then the unit would just be minutes to the negative first, or per minute. Yeah. Anybody have any problems getting to that? All right, so that gives us our rate constant. And then if we wanted to find the half-life, the equation is just 0.693 divided by our value for K. And then what did we get for that?
88.85 minutes.
Right, and then it'd be 88.85 minutes, perfect. And then whatever your K values unit for time is, then your half-life has to be the same thing. So let's turn this off. All right, so let me give you another way of looking at this. Let's go to that. Okay, so do we see this graph up here?
Yeah.
All right.
Yeah.
Yeah.
Okay, so if we look, I know this one kind of tells you where it kind of shows everything. So we start with A naught, and then it takes 1 unit of time for half of it to go down. Right? And then we take a look, it takes another same unit of time to 2 for the next half to go down. And then for it to get cut in half again, it takes the same unit of time. So because the unit of time is always the same between each consecutive half-life, that's how you know it's first order. And notice here, the X and Y axis don't deal with natural logs of anything, and that's why we don't get a linear line. Right? So if we graph the natural log of A versus the natural log of A naught, that's when we get a linear line for KT. That's how you know it's first order. However, if you're just looking at the concentration just versus time periods, you're going to get this logarithmic graph that you see here. And every time the amount gets cut in half, the unit of time should be the same. Right? That's first order. That is the one that's going to be most tested in kinetics. Right. Is there any questions about first order? So let's go back to the notes then. All right. Second order, the only thing you need to worry about second order, again, because they're not going to be testing it, the only thing that they might test is this line about half-life. That unlike zero order, where the half-life gets shorter, the half-life can get longer every time. All right. Oh. All right. We all good?
Yeah.
All right. Okay. All right. So then we'll talk about reaction mechanisms today, and then after we get through mechanisms, we'll stop for today. All right. So basically, most reactions do not occur in one step. So even though we write out a formula and one like equation, that doesn't mean it actually happens just like that. There's usually several steps called. We call them elementary steps. All right. One of the steps is always called the slow step or the rate determining step or the RDS. Think of it like this. Who's ever driven on the turnpike before? Either you or like with your parents, a show of hands. Turnpike, anybody? Anybody want to take a guess what on the
Yes.
turnpike would be considered the rate determining step?
The right lane.
Nope. What do you have to go through on the turnpike to like get on or off of
The
it?
acceleration lane. The toll booth.
The toll booth, right? You guys could be moving, you can be driving at, you can be 90 miles per hour down the turnpike, and then you have to get into the toll lane and you have to slow down to get through the toll booth, even if it's, easy pass. That step is your choke point. That's the rate determining step. Like if you go to a theme park and everybody can like get out of their car and everybody can walk up to the gate, but if you have to stop to get your ticket scanned and then after you get your ticket scanned, you can run around again, scanning your ticket is the rate determining step. Right, you can think of it like that. So if you are found in one of the elementary steps, but you are not part of the overall reaction, you are an intermediate. And we don't let intermediates appear in rate laws. Right. If any species is found in the beginning of the equation and it's also a product, then it's a catalyst. Right. And if you are given a set of elementary steps, you can write the rate law equation from the rate determining step. That is like the only time you can just look at a reaction and say that's what the rate law is. If you have the elementary steps in front of you and you are told which one is the slow step or the rate determining step. right? And then the mechanism must add up to the overall reaction. So if you add all the steps together, you must produce the overall reaction. Okay. All right, so let's take a look at this one. So we're given the overall reaction, ID any catalyst or intermediates, and then write the rate law for the reaction. So we have our 2 steps below. Oh. Right. So if we look here, chlorine and chlorine, okay, shows up as a product in step 1 and a reactant in step 2. So would this be a catalyst, or do you think this would be an intermediate?
Catalyst.
Catalyst.
I'm gonna say it's an intermediate.
So, okay, so we produced it in the beginning and then we immediately use it up. So it wasn't there when
So
we
it is
started and it's not
catalyst.
there when it ends.
Yeah. So it's an intermediate.
So this is an intermediate because it was produced in the middle of the process and then it was used up in the middle of the process. Why won't you erase? Okay. So catalyst would be anything that starts as a reactant and then finishes as a product. And we don't have anything because nothing on this side over here ends up over here. So there are no catalysts for this reaction, okay? And then if we add them together, let's see what we get. All right, so if I take these 2 steps to add together, if I add NOCl2 or NO2Cl and NOTCl, if I add the 2 of them together, I get 2 NO2Cl. If I add the NO2 and the NO2, I get 2 NO2. And I have 1 Cl2 and I have 1 Cl2. And this chlorine and this chlorine are on opposite sides of the arrows. As intermediates, they cross themselves off. Okay. So we know that it adds up to the overall reaction. So we know the mechanism is okay. And then for the rate law for this reaction, we just look at the slow step, all right? And we can write rate equals K. All right, and we know it's gonna be NO2Cl. And then do we include the chlorine in the reaction?
No.
No, because the chlorine is an intermediate. We can't write intermediates in the reaction. So that's the rate law for that.
You wouldn't include a catalyst in a reaction either,
No,
right?
we wouldn't include, nope. We won't include the catalyst either.
Okay.
Because the catalyst, we're going to learn about what the catalyst does like later on this week. We'll talk about what the catalyst does. The catalyst actually doesn't help the actual reaction occur. It just lets it happen fast. Not the same thing. It's not involved in the actual reaction. All right. Mouse. All right, so let's take a look at another one. All right, so we have the following mechanism for the decomposition of ozone in the stratosphere. So ozone plus chlorine produces oxygen and chloromonoxide. Chloromonoxide and oxygen produce chlorine and O2. Okay, intermediates, catalyst, and the overall reaction. So what do we think we got here?
Chlorine is a catalyst.
Yeah.
Yes, chlorine is a catalyst because it's in the beginning of the reaction and it's produced at the end. Excellent.
And chlorine monoxide is the intermediate.
You got it. And then if we added our steps together, right, what would our rate law look like? Or so what would the reaction look like? What would the reaction look like first?
Is it just O3? Never mind. I
Ozone
know.
plus oxygen yields to O2.
You got it. So let me write that out, right? So we have O3 plus O, because these guys go away. And on the other side, we have two O2s. Right. And can we figure out, just by looking at both of these reactions, are we able to determine what the rate law would be for this one? Why, yes or no, and then why or why not?
No, because it doesn't tell you which one's the fast one and which one's the slow one.
Beautiful, right?
Yeah.
Because there doesn't tell you who the rate determining step is, we're not sure. So you can't predict what the deal is for this one. But, all right, environmental fact, that's why they say like burning styrofoams and things like that is really bad for the environment, and releasing CFCs, because CFCs are carbon fluorochlorides, and the chlorine gets into the ozone and it is a catalyst to break apart the ozone. So there's your cross-curricular activity for the day. Save the earth. Don't dump your chlorine in space. Right.
Wait.
For all of you and your excess chlorine containers, don't be dumping them in space.
I have a lot of this.
Yeah. All right, let's try another one out. We got like two more. So here we got a rate law. We have a reaction. We're given the rate law. Does this mechanism work for this? Yes or no? So we're given a slow step. So what does the slow step? What does the slow step tell us?
That it's the rate determining step.
Right. So the slow step gives us the rate determining step. So if we look at the slow step, all right, we have NO and Cl2. All right. Neither one of them are intermediates or catalysts, so they are both allowed to be in the rate law. So we would write our rate law as rate equals K. This is atrocious. NO and Cl2. Yeah. Thank you. I'm glad that I can provide you with humor at this time of whatever. But we can see that that matches with this. So do we agree? Yes or no?
I agree.
I agree. Okay.
Yeah. I
Second
concur.
part. If we add these two equations together, do we get this that I just drew this beautiful line through instead of underlining? Now I made it like a fish.
Yes, you do.
Awesome. All right. So before we move on, real quick, how do we can see all of our faces here? Oh, Brenna has a nice sunset, and Caleb is absent, and Luca is just the word Luca. Hey, Brenna. Seriously,
I'm not even out of bed yet.
well, not going to be surprised. I'm not going to throw that.
Brenna, write your technical paper.
How are we doing with this? Any questions in all seriousness?
Get it?
Fine.
I'm fine.
I'm
Good.
dead.
Jose, we all right? Or are you just shrugging your shoulders? Beautiful. 2 thumbs up.
Jose, unmute yourself. God.
There you go.
Thanks.
Happy
It's
birthday.
Jose's birthday. We
Yeah,
should
it's
sing him
birthday,
happy
Hey,
birthday.
Jose.
somebody said it's your birthday. Is that true,
Anthony, I
Jose?
said that literally
Yeah,
like
How old are you now?
17.
Well, when
Happy
you,
birthday.
Jose, when you
Happy
come back to
birthday.
school, I expect cupcakes for the whole class. I'm just letting you know. Your grade depends upon it. I like funfetti, okay?
Okay.
Just something to look forward to. Get back to school and feed fast cupcakes. All right.
Eric, you look like a goat with that bathrobe.
Thank you.
Yeah,
Anthony, you look like a goat with that 1 + 6t.
Eric, I think you kind of need a pipe that blows bubbles.
Why?
Like a Sherlock Holmes thing with that robe on.
Yeah.
Like you could
Yeah,
be
it's
solving
really
mysteries in 1800 England. All right, so we're talking about these quick terms, and then that's it. Okay. So it's called molecularity. Oh. All right. If something is unimolecular, it involves one molecule. All right. Bimolecular involves the collision of two species. And termolecular involves three species. And if you heard something about somebody going around the track, I'm sorry, Zach is playing with cars next door to me. If something's unimolecular, you can usually think about something just decomposing. All right. So otherwise it's one thing, like hydrogen's not going to just all of a sudden turn into something else. It's probably just going to decompose into something. All right. Bimolecular is two things. It could be two of the same molecules running together. So I don't know, O3 and O3. It could be two different molecules running together, O3 and single oxygen. And then termolecular, again, three species. It's two of one and one of the other, or three of, three different things. We don't see things larger than termolecular. Anybody want to take a guess why?
Because that's really confusing.
Well, think like this. A reaction occurs when two molecules do what to each other?
They bond.
Well, they have to like collide, right? They have to basically, bounce together. All right. So you have two molecules that are going to bounce together. Right? How many times has anybody ever tried to give a high five to somebody and it's been like a really awkward high five?
Yeah.
Yeah.
Right. Well, if you don't give the high five perfectly in chemistry, the molecules don't react. So if you have three people trying to give each other a high five at once, right? Just imagine how difficult that is. In chemistry, you need to high five between three people to occur perfectly for the reaction to occur. So termolecular reactions aren't very common. And to get four things to collide just perfectly is basically impossible. So that's why there's nothing above termolecular. All right.
All right.
So the only thing left is the collision model, and we'll save that for another day because this was fine for today. So here's what I'm thinking about how we'll run this week. Oh, first off, how was Zoom for this? Was Zoom okay this time? If we did it again, would you prefer like something later in the morning, afternoon better?
Later, please.
I'm gonna be more responsible.
If
Right, you're getting called out.
Animal Crossing until 5 in the morning.
Always better.
7
hasn't
o'clock,
arrived yet. Okay.
What time, Eric?
like 7. I don't know.
Wait,
7?
7 or
Oh wait.
No.
No, Eric, no.
Shut.
how does like 10 in the morning sound?
That works.
That's great.
Good too.
All right, do you want to do this Wednesday or Thursday? I think we should do Wednesday, 10 in the morning. Does that work?
Okay.
Yeah.
Okay.
Oh, good. All
That
right,
works.
so
Just
we'll
make sure
finish-
law doesn't do anything.
I'll text
Yeah,
the
that's it.
AP group and let them know.
Okay.
So tomorrow I'll give you guys some practice on half-lives and molecularity steps and like rate laws.
Mhm.
Wednesday we'll do the notes. Thursday we'll do practice problems. Friday we'll do the same thing we did last Friday. We'll just do like a mini test just on half-lives and the molecularity intermediate stuff. And then next week we'll review for everything.
Okay.
And then I guess, we'll test, I don't know, not next week, but maybe like the week after that, Monday or Tuesday.
All right.
All right, Brenna, your background creeps the hell out of me. I just want to throw it out there. And then the more I find out about the AP test itself, the more I'll let you guys know.
So you don't know like the format or anything?
I've heard a lot of conflicting reports, so I don't know for sure. So I don't want to
I
tell you
don't
guys.
think College Board knows the format of the test right now.
Mm-mm.
Yeah, they said they were going to announce more stuff soon. I was amazed that they announced the fact that they canceled, the last 2 units, which we already did.
I have it in calc too.
Yeah, last class, everybody got something canceled out. So, yeah,
Canceled in calc.
it kind of is what it is. But the more I find out, the more I'll let you guys know. All right?
All right.
All
Thank
right.
you. Wow.
No problem, guys. I hope to see you guys in person soon. And Jose, happy birthday.
Thank you.
And don't forget that you owe us cupcakes when you come back to school.
All right.
We're going to hold you to it. And be good and stay safe, everyone.
Stay home.
Alrighty.
Stay home.
Hey, Mr. Falcon,
Alright.
Yes,
can you explain concept check 3?
sure.
Just a justification part.
I
Sorry.
can. All right. If you guys want to head out, feel free. If you want to stay on, that's also fine.
Okay, bye, Mr. Law. I'm gonna go back to sleep.
I'm not Mr. Law. See you later, Carson.
Like,
I'm a dip. I got other homework to do.
Yeah. All right. Give me one
Bye,
sec,
Madison.
Brandon. All right. Which one? Concept 3?
Yeah.
All right. Let me do this. How do I do this? All right. So if the rate law for this reaction is, you guys are seeing it, right, on the screen?
Mhm.
Yep.
Okay. Oh. Okay. So this is the reaction right here. All right. And then they're giving you the rate law off to the right, which you go and highlight in horrible, horrible font. So is the mechanism that follows consistent with this? All right. So the first thing we need to know is if we add the 2 equations together, right, these 2 down here, if we add them together, they have to produce this guy up here. Right? They have to make that same reaction again. All right, so NO plus NO, all right, does give us 2 NOs. All right, and that takes care of both of these. All right. The Cl2, there's nothing else, so we get plus Cl2. All right. We have NoCl2 down here, but that gets removed by this because these are intermediates. So these guys go away, so we don't have to worry about them. And then on the right, the only thing that's left is 2 NoCl. So does this right here match with this? And the answer is yes. So the mechanisms work because they produce the overall reaction. So that's the first thing we have to look at.
Oh, so that's basically the explanation. It just
Right.
works
So
like that? Okay.
and the mechanism has to do 2 things. The mechanism has to, for this question, it has to A, line up with the overall reaction, which is this guy up here. And does this mechanism also make this rate law true? So right now we satisfied the first part. We said If you add these two together, you get this bottom reaction. This bottom reaction is the same thing as this. So that works. The other part is to look at the rate law. So the rate law is KNOCl2. The rate law can be produced if we know an elementary step. Well, we know these are the two elementary steps. And we know this first step is the slow step or the rate determining step. And that step is how we can write the rate law. So if we look, the rate law can include any intermediates or any catalysts. And it doesn't include intermediates or catalysts, because we know that. And if we write it out, it would be NO to the first power and Cl to the first power. And that's what they wrote up here. And because those match also, we know that this mechanism works because it A, produces the overall reaction, and B, it also satisfies this rate law equation.
Okay,
Okay.
that'll be good.
Anything else, guys? Oh, all good.
Do you have any second order examples, problems?
Of which ones?
Like,
I'm
you
gonna
know that
hop off.
second order slide
No
that
problem.
integrated half-life, all
Yeah.
that stuff,
Yeah.
or the first order? Because I don't think I'm getting a
Yeah,
little
yeah.
bit lives.
Give me a sec. I'm looking through your homework, because I'm sure there are some in your homework that are half-life. So I want to make sure I try to find ones that are for first order only, because there's no point in doing the other ones really. Rate laws, rate mechanisms. Where the heck is half-life? Brandon, I can't find any of it off the top of my head, and I want to keep you guys waiting forever. But I will look for some, and then I will let you know what I find, and I'll post some stuff to the classroom.
Okay.
Okay, and I would assume too that there's definitely some in Albert that deal with first order half-lives. Nice mustache, Eric.
Thank you.
No problem. Look good on you, man. All right. Anything else, guys?
And that's it, I think.
All right. See you later. Jose, enjoy your birthday, man.
Thank you.
All right. Bye. See ya.